Let's talk about intermolecular versus intramolecular forces. Now, intramolecular forces you've already heard about, even though you may not know that's what we were discussing, whereas intermolecular forces are new. And so let's talk about both of these in this lecture today. So inter and intra, what do these mean? Well, if you compare them with interstate versus interstate are things such as Highway 40, which connect various states to each other, whereas an intrastate system is all of the different highways or the other roads that connect different pieces of the state to each other. Okay, so whenever we are thinking about these in terms of inter and intramolecular, we're talking about either the forces within a molecule, those being intramolecular, and these are your covalent forces or your ionic forces, as compared to intermolecular forces, which are simply forces between molecules. Now, it's to be noted that these forces are typically weaker than your covalent or your ionic forces, and in these videos we'll try and figure out why that might be. So, what's happening here? What are intra? What are inter? And let's talk about them. So in doing so, let's talk about them as they apply to water. H2O, dihydrogen monoxide. On the left, you see ice, which is a solid, and then you see liquid water, and then you see steam, which is a gas. And so as water transforms from a solid to a liquid to a gas, it's going to require differing amounts of energy to make that transformation. So which one requires the most energy? I am glad you asked. So here it is. Here is an energy diagram for water. And so what you're seeing is on the bottom axis, this is where you're adding energy in the form of heat. And so heat is increasing from left to right. So if your sample is starting out as ice at negative 20 degrees, it's going to increase in temperature until it hits 0. And at 0, that's a really fun state. You've got an equilibrium going on where ice is converting to water. So is dihydrogen monoxide a liquid or a solid at 0 degrees? Yes, it's both. It's slowly transforming. The second all of the ice has been transformed to water, now any energy you add into the substance will change the temperature instead of changing those forces that are holding the ice and the water or the water together. So then water increases in temperature until it hits 100 degrees, the boiling point of water, and then water is translated to steam. And then steam, you add any more heat, guess what? You're just heating up the steam. Okay, and so in looking at this diagram now, what can we learn about what that question we just asked was which chain requires the most energy? And so look at the blue line and compare it to the orange line. Which one's bigger? The orange one. So what that means is it takes a larger amount of energy to turn water into steam than it does to turn ice into water. Now, why is that? Solids, they have a defined shape, a defined volume. They're rigidly held together, the molecules are. With a liquid, there's flow, there's movement, you've got a defined shape, you've got a defined volume, it fills the shape of its container, whereas steam, it gets to do what it wants. It's moving really, really, really stinking fast. It fills the shape of its container and it does not have a defined volume. So when we look at our energy diagram, that's something that relates to why we see the large difference between water and steam energy, the energy it takes to turn water into steam, and the energy it takes to turn ice into water. Because when you're going from ice, it's rigid, molecules are slow, but when you turn it into water, the molecules are still connected. They're still interacting with each other in space. And that interaction are these intermolecular forces, which we're going to talk about. When you go from water to steam, there's so much space between molecules and they're moving so fast that the individual molecules don't really have time or availability to interact. And so it takes a whole lot more energy to get rid of those forces, to remove those intermolecular forces, break away from each other, and turn into steam. So that's why you see such a large difference in these enthalpy values, that of heat energy, between going from 6 all the way up to 40 kilojoules per mole. Something of interest, though, is notice that breaking bonds requires even more energy. So going from water, converting that into hydrogen and oxygen gas. So that's a large amount of energy. And so why is this? Well, let's think about this structure. You've been looking at Lewis structures, and so here's the Lewis structure of water. So what types of forces are present? Covalent, you know that. Your hydrogen is covalently bound to your oxygen, and then you have those lone electron groups hanging off of the oxygen. But it being covalent, is it polar or nonpolar? It is definitely polar. And because of that, you're going to have a partial positive charge on the hydrogens and a partial negative charge on the oxygen. And so those different dipoles are going to make it so now we can have intermolecular forces that are going to be characterized by that interaction of the oxygen with hydrogens on other molecules, or the interaction of hydrogen with oxygen on other molecules. And so you can see here how a central water molecule might be interacting with 4 different water molecules all around it. So this is just how they line up. And you can picture this happening in ice very rigidly, forming a crystal or a very good complex lattice that's going to give water its properties. Whereas in a liquid, you still have these same interactions. It's just as the molecules are moving, they're not rigidly bound. They interact. The hydrogens of one molecule interact with the oxygens of another molecule, but then they move on to another molecule. It's okay, but the molecules are definitely still attracted to each other. And that is called your intermolecular force, the force between molecules. All right, so let's look again at these enthalpy values then. Your solid to a liquid didn't take a lot, but now liquid to gas, large, because picture these same intermolecular forces happening within a gas. How much time does each oxygen have to bond with the hydrogen of its neighbor? Not much time at all. I picture that as like the speed dating. No real good connections can be made in the gaseous phase. And so in order for to hold them together, it would take a whole lot of energy. So that just doesn't happen. So in order to overcome these forces, picture the liquid here. You've got them all connected together, and they're held pretty strongly by this interaction between oxygen and hydrogen of its neighbor. In order to overcome that and force them to no longer interact, it takes a lot of energy. Okay, I think about this as moving from a good neighborhood. You've got all these bonds, all these connections. You don't want to move on, or graduating from college, whatever it may be. That is your intermolecular forces, your attractions to those around you. Whereas breaking bonds is completely different. It takes a whole lot more energy. That's almost like breaking bonds within a family structure or something like that. It can be harder, not always, but sometimes it can be very hard to fracture. And so with hydrogen connected to oxygen, that is a covalent bond. It is super strong. It's holding it so rigidly, whereas it's more of a force for the hydrogen with the oxygens around it. Why? Because here, it's already in a molecule. It's got the satisfied octet, the oxygens, those electron configurations, those molecular orbitals, they're all very happy and very satisfied. And so when we're talking then about breaking them, that's much harder than breaking the connection between a hydrogen on this molecule and an oxygen on another. It's already happy with one oxygen. It's like the force, the attraction with a neighbor is not required, but it's easier to fracture that because it's already pretty satisfied within itself. So you've got your intramolecular forces, which are the strongest, and your intermolecular, which are not as strong, but help us kind of characterize and understand attractions between solids, liquids, and gases. All right, here's kind of a summary slide for intramolecular forces, which we've already learned about. You've got your nonpolar covalent, your polar covalent, and then you've got your very polar, which are going to be your ionic bonds. And so the strengths of each of these bonds varies depending on, yes, what elements are involved in the bond, and then also the bond type. And so these intermolecular forces, though, are very strong, and they are holding these atoms or these compounds together. Now think too about how electronegativity plays a role in these relationships. And so anytime you have very, very large electronegativities, those are going to be your polar compounds. Anytime you have very small electronegativity difference, those are your nonpolar or your covalent compounds. Okay, so let's look at the first intermolecular force. Let's say we have dissolved some sodium chloride into water. We know that sodium chloride is NaCl. But when you dissolve a whole bunch of salt into water, it's not like you just have one individual molecule of sodium chloride, you have multiples. So sodium chloride can interact with the water, or it can find other sodium chlorides and interact with it. So when that happens, the latter, your sodiums are going to line up with your chlorines, and your chlorines are going to line up with the sodiums. And so they're going to find the opposite. The cations are going to find the anions, and the anions the cations. Whenever they do this, that interaction is termed an ion-ion interaction. That is our first and our strongest intermolecular force. In fact, this force is so strong that actually the individual ions can separate, which we know they do, and then they can now are free to form new ion pairs if they wish. That's why when you throw sodium chloride into water, you get sodium ions and chlorine ions. They typically don't stay bonded. Now they're free to interact with water, and they're free to interact with other chlorines. But these are intermolecular forces, and so they're called ion-ion interactions because you're using ions and interacting them with ions. And all of these names kind of are like that. They're kind of a little like, oh, that's obvious. The next force, we've got a polar compound here, hydrofluoric acid, which hydrofluoric, remember when we talked about dipoles, it has a dipole, meaning if you were to draw the dipole for hydrofluoric acid, hydrogen is partially positive, fluorine's partially negative, you would draw an arrow with the tail next to the hydrogen looking like a positive and an arrow drawn toward fluorine. So since it has a dipole, they are going to interact, and they're going to interact such that the fluorine is going to interact with the hydrogen on a neighboring atoms or molecules. This interaction now is called dipole-dipole interaction. This force is super strong, but it's not as strong as ion to ion. And so whenever we're talking about dipole-dipole interactions, that's simply when you have two polar covalent compounds that come in and interact based on where the poles line up, and it lines up to maximize attraction and minimize repulsion. And so that is also stated here. And so the idea is they're going to line up all like this. Now, whenever you've got a solid, it's going to line up and kind of still be rigid. Whenever you have a liquid, there is fluidity to this, but the idea is the two polar molecules are mainly going to be interacting with each other through this dipole-dipole interaction, meaning we're minimizing repulsion, maximizing attraction. Now, this is, like I said before, a whole lot weaker than the ionic bonds, and this does change for solids, liquids, and gases, because think about that. If it's going to be rigid, or if it's going to be kind of flowy, or if it's going to be moving at high velocities, it's a lot weaker in the gaseous phase than in the solid phase. All right, what about this one? What's going to happen here? This one I think is the hardest for students to understand. We've got two compounds, and they are the same compound, but they are both nonpolar covalent, which means, do they have a dipole? They do not. They're going to be nonpolar. So what happens when they come together? Are they going to interact? Are they going to want to repel? Are they going to want to attract? What's going to happen to the electron cloud around each of these fluorines? Because fluorines are going to have a whole bunch. Each fluorine has, 6 electrons floating around it, and that's not counting the ones in the bond between the two fluorines. Do you think their interaction is stronger than the ion-ion, weaker, etc.? And so it's going to be pretty interesting. So what's going to happen is, because like I said before, each fluorine has electrons around it, electrons are obviously going to want to repel, and the nuclei are obviously going to want to attract. So the electrons are going to shift such that each fluorine molecule now has a partially negative side and a partially positive side. How does that work? Well, the electrons, it was, a single bond in the middle with 6 electrons on each fluorine, and maybe some of those electrons shift to be on the fluorine on the right in both instances. And now you have what's called a partial dipole or an induced dipole, meaning even though fluorine gas is not supposed to have a dipole, it is nonpolar. We know this. We can force it to temporarily have a dipole that's based solely on how the electrons are distributed in that given second of time. And so that's what's showing here, is when two molecules come together, the electrons on one fluorine are going to shift away from the other fluorine. That way you have a partially positive attracted to a partially negative side of the other compound. And this force is called an induced dipole, because we are temporarily inducing a dipole in a molecule that did not natively have a dipole. Here's another example using helium. Helium has 2 electrons around it. So what's going to happen to those 2 electrons? It doesn't have to be a compound. They can partially move on each of them when they come near another nonpolar compound. And that's called an induced dipole. Because like you can see now, the helium atom, even though it's just a single atom, the electron density within the individual atom is more on one side of the nucleus than on the other. And so you have temporarily induced a dipole, so the intermolecular force describing the attraction between 2 helium atoms is induced dipole, induced dipole. And that's good because if you simply said, helium, it's nonpolar, there are no forces between helium atoms. That'd be bad because then if you just have like a helium liquid or something like that, that means there's no attraction. What's going to hold that molecule together? Nothing, okay? Or mercury. You know how mercury is really pretty? It actually has very, very strong intermolecular forces, at least more than it should. And that's because a lot of this induced dipole is really holding it together. Okay. So here's some more information on this type of intermolecular force. First off, I call it induced dipole. You can also hear it called van der Waals force. You can also hear it called London dispersion forces. Same thing. They're all the same thing. So these forces are between nonpolar atoms or molecules. Anytime you have something that's nonpolar that comes in contact with another nonpolar compound, you're going to have your electron density rearranged to form an atom or a molecule that has a momentary dipole or a slight change in polarity. Therefore, it's called induced. This is very, very weak and very, very short-lived. Something to note, though, is that the more electrons you have, your greater your odds of polarization. Meaning, if we look at helium, it only has 2 electrons. But if we go down the periodic table, neon, argon, krypton, xenon, radon, we're getting more and more electrons, which means more electrons you have, the more they can move to one side of the atom to the other. Therefore, you're having increased strength of these forces. You'll have a larger induced dipole or a larger van der Waals force amongst the molecules or atoms. What now about hydrogen bonding? So hydrogen bonding is the last type that we'll discuss. And basically it's a subtype of dipole-dipole interactions because in order for you to have this hydrogen bonding, you need to have a hydrogen and you need to have it attracted or attached to a very electronegative element. And those electronegative elements are oxygen, nitrogen, or fluorine. So if you have hydrogen attached to carbon, it doesn't count. Okay, you can't hydrogen bond in that situation. Your hydrogen has to be attached to something that's very electronegative, and it needs to be noticing the neighbors that also have that electronegative element. Okay, if that happens, very, very strong. What you see here is water where your hydrogens are attracted to the oxygens. Very strong subtype of dipole-dipole interactions. Intermolecular strength. So it really depends on what are the molecules or atoms that are interacting. You've got ion to ion is the strongest. You've got dipole-dipole is next, with hydrogen bonding be the strongest of those. And then you have your induced dipole being the weakest. Here's a good summary slide that describes all those types and then introduces us to a couple more. That being ion dipole. It kind of makes sense that this would exist, meaning you've got water, which has a dipole, and then potassium. Let's say you threw some potassium chloride in a solution. That's going to release potassium ions. Well, is water going to be attracted to potassium? Absolutely. Do we describe that as dipole-dipole? No, because you have dipole attracted to an ion, so it's ion-dipole interaction. And so this is just basically naming the interaction based on the individual species that are neighboring or making up that force. And so it's ion-dipole. An ion is attracted to something that is polar. And then we talked about dipole-dipole, hydrogen bonding, and then we also could talk about a dipole with an induced dipole, meaning we have something that's polar and it's being attracted to something that is nonpolar. That's going to actually help us figure out solubility a lot, because if a nonpolar compound, which should not dissolve in something polar, if it does, that means the attraction was strong enough between the polar compound and the new dipole that was induced in the nonpolar substance. And so this idea of how does stuff interact is going to help teach us a lot, like boiling and melting, which we talked about before, but also solubility. Like dissolves like, we'll talk about that later. If something is similar to it, if you have a similar type of intermolecular forces, they're going to be pretty dissolved, they're going to be pretty soluble within each other. And so this type here that you see between water and fluorine gas is a dipole-induced dipole because you've got a polar compound and a nonpolar compound. And then obviously induced dipole for that last substance. When we're discussing intermolecular forces now, we're not just asking which ones are present, we're saying which one's dominating. Whenever I ask a question of maybe who dominates in a sport, I think personally of Michael Jordan. He dominated basketball. And so what did it take for him to dominate? There's lots of factors. You've got his interaction with his players, his team, his coaches. You've got his interaction on the court, off the court with his practice and his work ethic. You have lots of components that go into making him who he was on the court. But sure, there were different parts of his performance that maybe led more to his dominance than others. And so it's going to be that same way when we are talking about these intermolecular forces. I may ask which intermolecular force dominates. Why would I say that? Well, let's look at the top compound. If you have water and potassium, the number one force that's going to dominate is ion to dipole. But are there ever going to be moments where we're going to induce a dipole in either of those? Sure, electrons do sometimes move based on how they come. What if the potassium accidentally aligned with the hydrogen just because of how it was aligned in space? Sure, stuff can get aligned just slightly, and now we have a slight dipole that's been induced. Is that what force is going to dominate? Absolutely not. It's not going to really play a large role in this interaction overall. It's not the dominant force. So what force is going to determine the strength of the water with the potassium ions? Ion to dipole. And so with this, we're talking about which one dominates. So typically induced dipole can happen in most solutions, but it's not going to be the dominant force unless you have two nonpolar compounds. And so whenever you think about these, think about ion strength and which one is the most dominant. All right, so that's kind of an intro to the idea of intermolecular forces. In lecture next, we will discuss how these forces play a role in things that we can observe. So if you're coming in person, just come to class. If you're attending lecture via Zoom, I want you to find these items before class. And it's just so you can do the fun activities with us. So I want you to find cardstock or paper or a business card, dish soap, pepper, toothpick, that's optional, and then 2 bowls that you'll fill with water. And so we're going to have some fun, but we're also going to talk about how these intermolecular forces play such a pivotal role in so many things that we can observe or see.